I'm working at Basler as Vision System Consultant, and today I would like to present you or explain to you how you can optimize your machine vision system by utilizing the FPGA as pre-processing device as it can be found inside of a frame grabber. But first of all, I would like to give you some key facts about our company Basler. So I'm coming from the German subsidiary in Europe, being here for presenting this explanation on how to optimize FPGA pre-processing. And we have above 800 employees right now, and we are a well-known brand in machine vision. And we have 35 years of experience with machine vision itself. So when you look over the globe, you see that we have a lot of subsidiaries all over the world looking into all of different industrial applications. So what I would like to explain in detail right now will be the different processing approaches there are, how you can use and how to develop for those approaches. And in a second step, I will go together with Sangwei through the steps of use case examples and what we have optimized by using an FPGA in these kind of examples. So when we look far back in time, we see Basler was founded in 1988. And then in 1997, it became a camera manufacturer, while it was already serving the market like the digital display inspection. Then in 2019, one part was acquired, that was Silicon Software, already having a lot of experience in FPGA pre-processing and using visual applets as a product for this. Shortly after that, Basler Korea was founded by acquiring 2 distributors. Now we are today here on the Korean Vision Show, where we have a lot of customers being interested in the different target markets we are focusing on. So when it's right now about the semiconductor, the factory automation and so on, it's very often about high speed. So these high speed markets, they have different cameras, high speed cameras, and this delivers a high bandwidth of data coming into the software system. And this data needs to be processed. So while this is a complete system portfolio, I will now today focus on the development of FPGA pre-processing and at the same time showing the different runtime hardware devices we have for this. This is of course supported by Basler Pylon and the frame grabber SDK. So we will now step into some slides explaining how to optimize the system. So what are the basics of the architectures, and then how to develop on this one, and then later on some bandwidth considerations regarding this. So when we look into the machine vision market, when it's about extracting the information out of the images, it's the CPU and the GPU being well known and very often being used for finding these details. But it's also possible using the FPGA as an architecture. The FPGA is very different to a CPU or a GPU approach. When we look into the details, we see in general, the CPU is really good in using the machine vision libraries there are in the market. You can work on standard bandwidth in that case, but when it's coming to very demanding industries and applications where a lot of data needs to be processed, the GPU is also an option you can choose, but the FPGA is very strong in complex calculations and it's completely independent of the host system regarding its processing. So when we go into the technical background, we see that the CPU and the GPU at the same time, they can work, but they can only work on a single instruction on single data. Or at the GPU side, you can also go for multiple data. But on the left side, it's limited in the bandwidth. So the more complex the task becomes, the lower the throughput in that case normally. On the FPGA, it's different because you can put your pre-processing task into the hardware, so in programmable hardware, And this approach is limited in its complexity, but its throughput can be exactly at the target level you are searching for regarding your application. So when we now, as a summary, take together that we here see different processing architectures, so the CPU, the GPU, and the FPGA. And if you want to reach highest performance, the best option is using all of these three architectures together as a team, because as a team, these architectures are really strong. So where can these architectures be found? So I think everybody is familiar with a CPU and a GPU doing the image processing based on the images that are here in the random access memory of your PC. But when you acquire cameras at high bandwidth, mostly you require a frame grabber. And these and all frame grabbers, they include an FPGA you can also use for your processing or pre-processing task. So the optimization I would like to explain is based on splitting the processing over the different architectures. So when it's now about how to utilize the FPGA, it's about what can I do? What can you achieve for your application and the solution on this one? So when looking into Visual Applets, it's a development tool. A development tool especially designed for FPGAs inside of frame grabbers. We have in-house 15 plus years of experience, and it's a very unique tool because it's a tool where you don't need any FPGA pre-knowledge. So a machine vision engineer or an application engineer can directly use this development tool in order to transfer a known processing or pre-processing task into the FPGA of the frame grabber. So the customer on its own, or we as a company, we can deliver a development service so that you can shift your image pre-processing from a CPU and GPU part into the frame grabber that is related to your camera being used. When shifting the image pre-processing into the FPGA of the frame grabber, you don't need a very strong CPU, or you can, for example, also sometimes avoid using a GPU, so you can reduce your system cost by shifting the pre-processing into the FPGA of the frame grabber. While it's a graphical language in order to process the FPGA, it's very easy to use. So as you can see here, you can use a simulation mode driven by a CPU to see what the FPGA bit by bit would produce as a result based on the data coming into the system. And its graphical operators you can connect to each other. Next to image processing, you can also do signal processing. So when it's coming to real-time tasks, you can move these real-time tasks also into the FPGA, because the FPGA is by nature a real-time device. And this graphical approach simplifies the FPGA development drastically. When you would use the normal state-of-the-art programming based on VHDL or Verilog, for the FPGA developers here in the audience, then it takes weeks or months to achieve something. But when you use Visual Applets, it's a much shorter time because of its abstraction from the hardware layer itself. So when we want to talk about the hardware being available, we can support Camera Link, Core Express 6, and also Core Express 12, and more to come in the future. So when we look at these frame grabbers for Camera Link, they have a potential output of 1.8 gigabytes per second, while the ImaFlex goes up to 7.2 gigabytes per second. The ImaFlex series, it's focused on Core Express 12, so one of the current standards that went into the market. So when it's now about the development for these architectures, I already explained this, that Visual Applets is a development tool to develop something that is running in the FPGA of the frame grabber. For the GPU and the CPU, you have different software approaches that work on these images, and the interfacing is always related to the host memory. So the frame grabber can forward its results into the host memory of the PC so that the PC can directly take over doing some CPU or GPU processing based on the known libraries or also on Pylon V tools, for example. When it's a GPU coming into discussion, it's very often used for AI approaches, so calculating the inferences on different images. So when you want to go for AI stuff, the GPU is normally the architecture that is chosen, but pre-processing tasks can still be maintained by using an FPGA. Later on, I will give some use cases. So now I will go to the interesting part, at least from my point of view. So we are going into the use cases. So real use cases where you achieve some benefits by using an FPGA. So here, I guess a lot of the machine vision engineers here in the audience will recognize a lot of different pre-processing functions. It's just an excerpt. We have much more we can offer to you, moving it into an FPGA. So it can be something like a blob analysis, real-time processing, object segmentation. It's very similar to the blob analysis. Even JPEG compression is possible inside of the frame grabber. So if you want to do some image storage, you can do a JPEG compression accelerated by hardware. Normally this is very CPU time consuming and makes the system more complex or more expensive. But in this way, going for the JPEG compression as a hardware acceleration, it's very beneficial to do so. So as one of the examples, it's a flat field correction. It's very easy to understand. So you need per pixel coming from your image, an offset and a gain. A lot of cameras and other frame grabber manufacturers, they already give some flat field correction approaches. But in a lot of applications, you need a customized version or even multiple sets that maybe are not supported by the hardware you're currently using. So then you can use the frame grabber. Here you see how it would look like in the FPGA. It's very easy to understand, very straightforward implemented, and you can change together with us exactly to the pre-processing function you require for your application. You don't need to use the one that is existing in the hardware. You can do your own version of this. And of course, it's reducing the CPU load in this case. So when you want to use the flat field correction to go from an inhomogeneous lighting, so the corners are darker, to a very homogeneous representation of your image, you can utilize the FPGA of the frame grabber. Now we come to a more complicated use case. Here it's the frame grabber being used as acquisition and at the same time pre-processing device. So the camera is delivering the data into the host memory, so you can build up a stack for stack processing. And then the stack is sent back into the frame grabber in order to do on the pixel stacks that are part of the image stack some pre-processing. In this case, it's a fast Fourier transform to extract the real result. Something like white light interferometry would be a good example for this kind of processing. The benefit is, in this case, the FFT, hardware-driven in the FPGA, runs much faster than in the CPU, and the customer could avoid using a GPU and using a very cheap CPU setup in this case. The next use case is very common. It's distortion correction. Distortion correction is normally one of the pre-processing steps in a system. And this pre-processing step of doing the distortion correction or the perspective correction, later on I will also show some details on a demo we have on this at the booth. You see here the distorted image. This is the corrected one. And the correction is completely calculated in the FPGA on exactly the precision level required with a very good interpolation in that case. And this reduces drastically the CPU load concerning the further processing of this corrected image. So here you can see the distortion, and this is getting corrected within the frame grabber. This is now one of the more complex use cases. It's about battery coating inspection for e-mobility. So with a lot of line scan cameras, you look at the material, and as you can see here, a lot of different defects are possible on this coating. When you see these small defects, you would like to do AI processing on this one, using a neural network, doing so. But when you look at the cameras and the required speed and resolution, you will see that each of these cameras will deliver 1.6 gigabytes per second. So altogether, these 4 line scan cameras, they deliver 6.4 gigabytes per second. And if you want to do processing, AI processing on 6.4 gigabytes per second in a normal system, in a very small system, would be the best case for reducing the total cost of ownership of such a system. It's a problem you need to solve somehow. So together with the customers, we looked into the image data. It's very cooperative image data in this case. So it's very gray material, and mistakes, when you use the correct lighting and everything, they become white or a little bit darker. And only these small regions of interest, they need to get inspected. So what does the FPGA do in this case? It's utilizing the FPGA for finding these potential defects, while in a second step, the GPU and the CPU take over. So the GPU only needs to classify these small regions, while the FPGA detects the region itself. So the GPU is doing the classification of the defects, while the CPU and the GPU do the rest of the task. And the CPU is only doing the decision making after all of this processing. So the FPGA brings the data down to megabytes per second for the GPU by just selecting the defect candidates, and then the classification is still done by the GPU, but the system footprint is much smaller, so the cost reduction is enormous in this case. This is done by the reduced load and the FPGA bringing the gigabytes per second down to megabytes per second in order to speed up the GPU process. At our booth, we have this demo. It would be a pleasure for us if you... I just wanted to... So here we have the demo also at our booth. If you want to discuss on this, feel free to come along. It will be a pleasure for us explaining all of the background. So here you see a line scan camera, one of these line scan cameras delivering 1.6 gigabytes per second at 200 kilohertz line rate and 8K resolution. Here we have some sketched battery coating defects that are transferred in full data into the frame grabber. Then the frame grabber is extracting the regions of interest and is forwarding it into our Pylon AI that is doing the classification based on a very small and cheap GPU in this case, while the FPGA, based on visual applets, is doing the hard pre-processing inside of the FPGA in the frame grabber. And then we have the classification of these defects so far. So the next use case is the Scheibenflug optic in an FPGA. So you see that under perspective, it's looking in there. Our optics already deliver a very good image, but then you need to do a distortion correction or the perspective correction together with a flat fill correction to get a proper image representation. So here you have the FPGA. This is a Scheibenflug approach of doing images, and then the result is coming here. So the 80% higher contrast, that's based on the optics, but then you have the real-time pre-processing in the FPGA, correcting the perspective problem of this one to a very nice image for the further processing. So it's targeting for reducing the CPU load by using the FPGA again inside of the frame grabber. The last example now is the blob analysis I already mentioned in the battery demo. And here we see a comparison in between of CPU and FPGA processing. So while we have a high CPU load and we can only process 17 frames per second of this 5 megapixel camera in the CPU. On the other hand, when we look at the FPGA, we reach the full target bandwidth of 215 frames per second while having nearly no CPU load. So here you see directly the benefit in numbers regarding the performance. It's 17 frames per second versus 215 frames per second that cannot be reached. So when it's about enabling FPGA preprocessing, think freely, accelerate your vision while reducing the system complexity. And if you have an application, it would be a pleasure when you come around at our booth for a longer discussion,